that work?
Mm-hmm.
It's not a good idea.
No.
So I noticed from the program I have an hour and 13 minutes. So I thought I would keep it under an hour. Okay, so at Caltech and with our many collaborators, we are trying to image the certain galactic medium, intergalactic medium, certain quasar medium in order to understand how galaxies form and evolve and the link with the IGM. Our ultimate picture after many decades of work we hope to make. Basically, we want to understand how Lyman alpha traces the IGM and CGM gas flows. And that requires ultimately decoding Lyman alpha. That may require a satellite. Oh, sorry. Then use Lyman alpha and other lines to map flows in and out of galaxies, to map the intergalactic medium, the filamentary connection between galaxies that articulate the structure of the universe, and ultimately to use it as a cosmological tool. One of the interesting questions in the last decade has been how do galaxies get their gas, and what is the importance of cold flows, and more recently understanding how cold flows bring in baryonic angular momentum. As a side, we would like to understand the connection between the flows around galaxies and the properties of galaxies. And a separate aspect of our work is to understand how galaxies evolve from the main sequence to the passive sequence. And we recently published a paper in which, we introduced a parameter called the star formation acceleration, which is the derivative of the star formation rate. You have to worry about the signs, but basically we're trying to understand how fast galaxies move on the star formation mass diagram, and therefore be able to ultimately connect the dots between various phases of galaxy evolution. So for example, main sequence galaxies, the very strongly bursting main sequence galaxies have recently gone there, suggesting that it's a quasi-equilibrium process, which is keeping galaxies on the main sequence. If you have any questions, you can ask me later. Okay, our main program, understanding mapping the IGM and CGM at low redshift. We want to do that from space. We have a prototype experiment called Fireball. It's going to fly next month. I'll tell you a little bit about that. Ultimately, we'd like to do that as a satellite. And then on the ground, the Palomar and Keck cosmic web imagers probing redshifts 2 to 7, ultimately with the red channel of KCWI. Basically, our methods are to do imaging spectroscopy, to build spectroscopic data cubes, to do very precision sky subtraction, particularly on the ground, where the most interesting CGM, faint CGM, and IGM are a small fraction of the sky. And then for the space component, we need new detectors, and we're developing those, in fact, flying a very high efficiency next generation UV detector on the balloon next month. Going straight to that, Fireball 2 is a reflight of a 1 meter payload that flew several years ago with a Galaxy spare detector, very low efficiency. We've retrofitted it with a new multi-object spectrometer, so like a DEIMOS in space, and 1 meter mirror, next generation UV detector. And we look at Lyman alpha that's redshifted into the balloon window, which is around 2,000 angstroms. That's around 0.7, redshift 0.7. This is some of the key players, and I want to particularly point out Erica Hamden, and who's leading it, the U.S. component, and Jillian Kine, who's leading the detector development, Shirley Nixad, who's helped develop the detectors at JPL. And it's actually in New Mexico. This is the spectrograph at the focus of the telescope, it's a very complex thing. It's a complete telescope with a complete guidance system that's hanging from a balloon that will ultimately be the size of the Rose Bowl Stadium, and it'll be very exciting. We have a set of masks that are on a rotating a stage, and we use fields that have been surveyed on the ground, mostly deep 2 surveys. Thank you, Sandy. And here's some of the masks in situ. To select those regions around 0.7 with lots of structure. Oh, and by the way, the balloon is now tweeting, following the footsteps of some people. And today, apparently, we unloaded the gondola shipping container, putting our flight mask into my spectrograph, and being amazing. So you can check out the tweet, follow the flight next month. Okay, the prototype of the Keck Cosmic Web Imager, the Palomar Cosmic Imager, was basically designed to look at CGM and CQM emission, and is also being used by guest observers as well. One of the results was this Lyman alpha blob that has these extensions and kinematic evidence for rotation. And the blob rotates, the filaments around them rotate in a similar way, lots of angular momentum in this gas. This is one of our faintest results. We then looked at an object that was discovered by Sebastiano Cantalupo and Xavier Prochaska. We looked at it with CWI and found that it looks like a rotating disk, very large rotating disk connected to a filament. And it looked like the kind of structure that was predicted by cold flow models that produce these large extended cold flow disks, or rotating structures, let's call them in-spiral flows, illuminated by the quasar. Then we reinterpreted another object as also a disk, and this is the intensity distribution. It's much more lumpy, but it shows this is the velocity map. We'll be showing a lot of those, and the model of that showing it's a good representation, at least with the resolution and sensitivity of PCWI. And you can make fits to various parameters, dark matter halo parameters, and the age of the disk and so forth. This was, we interpreted this in the context of a cold flow in spiral. One of Avishai's and his group's models is shown here, showing the surface density, the azimuthal velocity, and the radial velocity. So one of the key of a spiral flow is that there's both rotation and inflow, radial inflow. And we'll get back to that in a minute. So we found four good examples of these, but the basic plan is to find more candidates and then observe them with KCWI to determine, one, are they disks? Two, do they show or rotating structures? Do they show evidence of spiral inflow? Do they show filamentary connections to the cosmic web? So that survey is called the Flashes survey. So we're observing, hopefully of order 50 to 100 quasars, looking for extended nebulosity around the quasar, and then characterizing the presence of shear, extended shear. This is a measurement of shear in detected features around quasars. It's like a projected angular momentum as a function of the area of the nebulosity, and here are a number of possible candidates for large rotating disk-like structures. And you can also see that the shear is correlated with the major axis, minor axis profile, suggesting that the systems that the disks, when they're inclined, show more rotation. Okay, so we're going to look at these with KCWI. KCWI has been commissioned, and the blue channel at least, and it offers a flexible selection of slicers and gratings, giving you anywhere from a resolution of 1,000 to a resolution of 20,000, and various fields of view and a slicer sampling. It's working beautifully. This is some of the team members. I want to particularly highlight the leadership of Patrick Morrissey and Matt Matuszewski, who made this thing work beautifully on the telescope. Here's a picture of the grating. You can see the calibration system, and then the beautiful camera built at UC Santa Cruz, led by Harlan Epps, Connie Rockesy, and great efforts by David Hilliard and Drew Phillips. Here's the instrument arriving at the dome. It was a perilous journey, but we made it. Turns out a screw got sheared. And the first set of calibration, the first set of commissioning data was done with only 2 connections to the collimator, which was swinging in the breeze, but it worked beautifully anyway. That's at the position at Keck 2 at Naismith. The efficiency is excellent. This is where we were trying to get, and this is the low resolution, medium resolution, both above that, and then the highest resolution is a little bit below that. But the throughput is excellent. First light image, M3 core, 2 10-minute integrations with the small slicer, high resolution grading. You can see beautiful spectra of some of the brighter stars. Here's one blown up to show it's indeed getting resolution of 20,000, which is unprecedented for a. What's that?
You don't. You have exhausted the 10 minutes.
Okay, done? What? How?
Well, you have to wrap up.
Okay, we'll wrap up. Okay, all right. Okay, so let me just show you 2 results. Okay, this is some objects, so I'll skip over that. All right, one result. This is a quasar. We see evidence for 2 rotating disks. The quasar is at the center, illuminating 2 systems. These are channel maps, and it's consistent with one of the disks being centered on the quasar and one of the disks being interacting with that other disk. And so that's the model. And you can do velocity maps. And if you just model as a rotating disk, it does a reasonably good fit, but not great. If you add in basically zonal radial flows along the axis of interaction, it does a much, it halves the chi-squared and makes beautiful fits to the data. So it seems to be suggested there are these zonal radial flows in the system where you might expect it from tidal interactions. And then this other object, nebulosity near this quasar, illuminated by it. Let me blow it up. That's we're going to focus on this. This is a looks like possibly a proto-galactic disk. It is rotating, in fact. It has these extensions. Again, looking like this, taking this as guidance, and you find that when you look at these simulated galaxies, that with the radial flow, you get interesting contours of velocity with respect to the no radial flow case. You just subtract out the radial flow, and we're actually seeing things like that. So here's a fit to this system. Just the disk. Here's the model. Here's the data. Not a very good fit. You add in a constant radial flow. Again, slightly better fit. Not so great. Add in a linearly varying radial flow. In other words, decreasing as you go toward the center. An even better fit. And then zonal, linearly varying radial flow. Really good fit to this system. So we think this is evidence that we're seeing not only rotation, but zonal radial flows, which are predicted by these cold flow models. And that is consistent with low dispersion gas in filaments coming in at least 1 and maybe 3 directions. So obviously I don't have time to go through all the results we have, but the instrument's working beautifully. I hope everyone has a chance to use it at some point, and thank you very much.
Again, it's a beautiful instrument. It's a pity that we have, we have almost exhausted time right now. Are we able to time for a question?
That's the situation with the software, such that the user has time to basically run into a pipeline, or do we have only the early stage where we tap into something special?
We have delivered a complete ready-made pipeline. So you will have data cubes 5 minutes after you take the data. Well, okay. Call me if you don't.